shall be continuing with the design of analog filter, and then we will implement an IIR filter from an analog design. Last time we were discussing about Butterworth filter. Today we shall be taking up Chebyshev filter of the first kind. Now, Chebyshev filter functions are like this, that is, in the pass band you have a definite width of the ripple like this, and then in the stop band it should go like this. Okay. The function is given by the magnitude squared equal to 1 by 1 plus epsilon square Cn square omega by omega p, where Cn is the Chebyshev function of nth order. We will just very briefly discuss about this function and then see how this meets our requirement for the filter. Now, Cn is defined as Cn omega is cosine of n cos inverse omega. Okay. Omega less than equal to 1. All right. So, how much is cos inverse omega? Let us assume this as x, then cos of x is equal to omega. Okay. Let us assume cos inverse omega as x. So, cos of x is equal to omega. So, cos of n cosine inverse omega, if I take, henceforth I will be writing just Cn, Cn plus 1 and so on, they are all functions of omega. So, what will be Cn plus 1? Cn plus 1 is cos of n plus 1 into x, okay, which is cos nx cos x minus sin nx sin x. C n minus 1 x, C n minus 1 omega will be cos nx cos x plus sin nx sin x. If I add them together, then C n plus 1 plus C n minus 1, that will be twice cos of nx cos of x. Do you agree? So, twice Cn cos nx is Cn into cos of x omega. Okay. So, Cn plus 1 becomes twice omega Cn minus Cn minus 1. Okay. So, this is a recursive relationship that we have got. In terms of Cn and its previous value, we can generate a new polynomial Cn plus 1. This is a polynomial in omega. Let us see what will be C0. C0 is, from definition, C0 is cos of 0 into something. So, cos of 0 is 1. So, C0 is 1. C1 is cos of 1 into cos of cos inverse of omega. So, omega itself. Okay. So, using these two I can generate C2. So, C2 will be twice omega into C1 minus C0, which is twice omega squared minus 1. Is that all right? Can you generate C3 from there? 2 omega into C2 minus C1, which means 2 omega into 2 omega squared minus 1 minus C1, that is omega. Okay. So, 4 omega cubed, correct me if I am wrong, minus 3 omega. Okay. You can generate a table of such polynomials by this recursive relationship. Okay. So, I would request all of you try to do that for 3-4 more steps. Try at home. Now, let us come back to some of the important features of this Chebyshev polynomials, which will be very useful for us. C0, suppose this is omega and this is C magnitude, okay. All right, I will just write Cn. What is C0? 1. So, let this be 1. So, this is C0 up to plus 1 and minus 1. We are considering up to plus 1 and minus 1, because cos x can be at the most plus 1, at the least minus 1, since the limit of omega is plus minus 1. So, we will study the behavior of this function in this range for the time being. Actually, when omega is greater than 1, it is given by cosh and cosh inverse omega, all right, hyperbolic functions, and that will also generate the same polynomial relationship. Okay. With the cosh function, hyperbolic functions also, you will get the same recursive relationship, all right. So, it is immaterial whether we are restricting within plus minus 1 or beyond. We will see its behavior within this range first. So, this is C0. C1 is omega. So, it is a straight line like this. This is minus 1. Okay. Then C2 is 2 omega square minus 1. So, when omega equal to 0, it is minus 1, and when omega is equal to minus 1 or plus 1, it is 1. So, it starts from here, it is a parabola going like this. So, this is C1, this is C2. Okay. C3, again 4 omega cubed minus 3 omega. When omega is minus 1, this is minus 1, it starts from here. Then when omega equal to 0, it is 0. So, it passes through this. Somewhere in between, it goes to positive plus 1. You can find out at what value of omega it goes to plus 1. This is C3 and so on. So, one thing you observe, for all these functions you can go on taking higher order polynomials. You will find a Chebyshev polynomial has this important characteristic: within the range minus 1 to plus 1 for x or for omega, the function c alternates between minus 1 and plus 1, all right, between minus 1 and plus 1, and then after that the magnitude goes up like this. The higher the order, faster will be the growth in magnitude, either it goes to the negative side or to the positive side. That means, if I take c squared, the magnitude will be tending to infinity as omega tends to infinity. Okay. Now, let us see a function which is epsilon square c squared. Epsilon square c squared will be, this range is scaled down, between plus epsilon square and minus epsilon square when we take c square, is it not? and since it is magnitude square, so it will be between 0 and 1. The least value it can have is 0. So square of this function multiplied by epsilon square will be alternating between 0 and epsilon square. Do you all agree? Epsilon square c squared, whether it is c1, c2, c3, they will be restricted within this. They can be, c0 is a constant, so it will be only this much. c1 it may vary just once. The number of times it varies will be depending on the order. Number of times it is alternating between -1 and +1. Alright. So if it is c3, how many times it is crossing over? Say once here, once here, once here. 3 times it is crossing this 0 level. If it is c2, it is crossing once, twice, 2 times. So number of crossover will be depending on the order. Okay. So what will be 1 plus epsilon square magnitude c squared? Once you square it, you need not put the magnitude. Okay. 1 over this, what will it look like? 1 by 1 plus epsilon square c squared. What will it be like? Its minimum value is 0, maximum value is 1 plus epsilon, maximum value is epsilon square. So it will be alternating between 1 and 1 by 1 plus epsilon square. Is it not? Depending on the order, it will be alternating. This is 1, and after that the magnitude goes on increasing, either on this side or on that side. If you square it, it will be always positive. So epsilon square c square, later on whatever be the order, will be going up like this beyond 1. When omega is greater than 1, it will be shooting up. So there it will be falling gradually. This is a monotonic fall. There is no ripple here. Okay. Ripples are only between 0 and 1. So here also the ripples will be within 0 and 1. So this will be the nature of variation of this function. Is that all right? So we have got a Chebyshev polynomial like this. Now what would be the roots of this? 1 by 1 plus epsilon square cn square, this is given. You find out what will be the roots. Once you know the roots, you can use bilinear transformation, substitute. Okay. Today we will also discuss another method, impulse invariance method. So this design is very simple. Once you know the roots of this particular function, that is, this is equal to, you write h s h minus s, s equal to j omega. Okay. Is not h or g, whatever you write, h j omega magnitude square is 1 by 1 plus epsilon square cn square. Okay. And we find this is having, this is h square, this function is having a characteristic like this. So what will be the corresponding analog filter function? In case of Butterworth filter, what did you do? You substitute s by j is equal to omega, if you remember, and then you find out all the roots. They are all coming on the unit circle, and then you take only left half plane roots, again form the polynomial that gives you HAS. Similarly here, find out the roots of this, take only the left half plane roots. They will be mirror images, right half plane roots and left half plane roots, they will come all in a symmetric position, they will be mirror images. After this substitution, you calculate the roots. In this case it will be an ellipse, alright. So they will come on ellipse. the roots may come like this. In case of Butterworth filter, they are on a circle. Okay. So, there are now the shape of the ellipse will be depending on the factor epsilon. Unlike a Butterworth filter, in case of Chebyshev filter, you have to specify epsilon, and depending on the value of epsilon, the shape of this will also keep on changing. So, the roots are not in unique position. Third order Butterworth filter will have unique position of the roots, whereas third order Chebyshev filter will have roots depending on the position of epsilon, value of epsilon. Okay. So, every time you have to compute separately the roots. Now, that is quite laborsome, but anyway there are shortcuts. Standard design books have given methods of computing it. One of the simplest methods is to find out the roots of the corresponding Butterworth filter. Okay. Sorry. Suppose it is a third order Chebyshev filter that we have got. All right. What will be the position of corresponding Butterworth filter? Then from the Butterworth filter, it is at 120 degrees, 180 degrees, 240 degrees, is it not? Because there are 6 roots for third order Butterworth filters, all right, corresponding to HAS into HA minus S. You forget about the right half plane roots, that corresponds to HA minus S. So, HAS is obtained by these 3 roots. There is a relationship, the ellipse that you get for the Chebyshev filter will be like this, and the real parts shift by a factor and the imaginary parts remain intact. All right, you just squeeze the real parts, then you know the locations of these. Okay. Then it is very simple. So, given epsilon, you can calculate a factor A, which you can evaluate from epsilon. We will not discuss in details the methods of computing these roots, they are very standard. So, it is basically tan hyperbolic A, which is the factor by which it should be squeezed, and A is something like 1 by sine hyperbolic 1 by epsilon, something like this. There is a relationship. While designing the filter, we will get into the details of this. And if you take the real part, squeeze by this factor, you get the real part of the Chebyshev filter. Imaginary parts you already know, so imaginary parts remain same. So, you can frame the polynomial and you can find out the corresponding Chebyshev filter. Okay. Now, the method by which we are trying to go from analog filter to a digital filter which was discussed last time, was bilinear transformation, or in general Adams-Moulton transform. You can go for higher order transforms. So, bilinear transform, which gave us S equal to 2 by T 1 minus Z inverse by 1 plus Z inverse. Okay. So, wherever there is an S, you replace by this, whether it is a Butterworth design or Chebyshev design, just a direct substitution of S with this. Now, let us discuss another simple method, that is invariance technique. Now, invariance technique is a totally different approach. You have the analog filter function, say I will take a simple function S plus A. Suppose it is a first order filter 1 by S plus A. If this is the filter, what is its impulse response? If I give a delta t input, it will be Laplace inverse of this. e to the power minus at into ut, that will be the output. So we now take it in the discrete domain. Given an impulse discrete function delta n, I should get a response, which will be a discrete version of this. That means the analog response is like this, e to the power minus at ut. I should get with this model a discrete version of this. What is this? This was HAS. What is that function which will give me this output? That means I want the output should be e to the power minus a t to the power n u n. All right. This is e to the power minus a t into n. So this is known as impulse invariance technique. That means corresponding to an impulse input in the continuous domain, if the output is known, then what would be the corresponding discretized output corresponding to an impulse input. Evaluate that, and that is the filter which I am going to substitute for this. All right. So there is impulse response in both the cases are matching. One is giving me only the discrete version of the continuous output. Now let us see what would be this like. Suppose I have an HAS equal to, these factors are 1 by say S plus Z1 into S plus Z2, these are the zeros and these are the poles and so on. I can always write this as some K1 by S plus P1 plus K2 by S plus P2 and so on. Depending on the number of poles, I have say Kn by S plus Pn. Okay. Then what will be the corresponding impulse response? It will be K1 by e to the power minus P1t plus K2 e to the power minus P2t and so on into ut. Okay. So my Hn will be the discrete version of these, which will be K1 into e to the power minus P1 into capital T whole to the power n and so on into un. So what will be the corresponding Hz? It will be K1 c to the power n is K1 by 1 minus a to the power minus Pt into Z inverse, is it not? Where e to the power minus P1t. Similarly, K2 by 1 minus e to the power minus P2t Z inverse and so on. That will be the Z transform. So let us realize it in the hardware domain. This will be represented by simple first order IIR filter of this kind. Suppose I have, what should I have? Some gain K1, okay, and then a feedback path e to the power minus P1t, okay, and then I can put the delay here or I can put the delay here as you please, a delay which is corresponding to Z to the power minus 1. So this gets added with the, is this all right? Is this all right? No. Where should I put the K1? K1 is a multiplier. Okay. Should it be this way? Put it as it is. Is that all right? Let us take 1 by, if it is 1 by 1 minus C Z inverse, all right. What is the corresponding structure? C, I can put a Z inverse here or here. So, whatever is the output Y added, okay, this is X and this is Y, all right. So, this gets added because this is Y by X. So, Y minus CZ inverse, if it is brought to this side, so that is being added. So, this is the elementary structure. Now, it is the C1, this constant which is changing, e to the minus P1t, e to the minus P2t and so on, and this constant K I can put here separately. So, it is like this, or you can put it at the end also, as you please. So, there are such blocks and they are to be added. So, what will be the net structure? Such blocks will come in parallel, is it not? So, it will be Xn you can have K1 adder e to the power minus P1t this will be say Y1. Similarly, Ki, I call it a general term, this is Yi and they are all added. There should be a delay here, that is good. Z to the power minus 1 e to the power minus Pit and like this. So, all of them will be finally added here to give you the output Yn. Is that okay? I could have had also the factors in this mode. Hz could have been obtained as HAS. Okay, let us see whether it is possible. HAS is S plus Z1 into S plus Z2. One may suggest this S plus P1 into S plus P2 and so on. I can write as product of the first order factors S plus P1, S plus P2 in the denominators, H1s, H2s and so on. Can I realize H1s and H2s in cascade? Can I put them? Have you understood the question? Now, because each H1s, each first order factor I can realize by an equivalent digital element like this, this is corresponding to a first order factor K1 by S plus P1t, okay, S plus P1, okay. So, can I now put such blocks in the product form instead of summation like this? Suppose I write in the form of products. Is it possible to realize this? What do you suggest? Our condition was we are replacing it, assuming that we are giving an impulse input, and that gives me an identical output in the discrete domain. Now if you put them in cascade, what will be the output of the first set? It will not be an impulse anymore. So you are not giving an impulse input, and that condition is not satisfied. So in the cascade form it will not be allowed. Is that all right? Now one may suggest another invariance that is step invariance. You can have any of the standard signals, keep that as an invariance, and then design a filter. Let us take once again a very simple factor, k by s plus a. Now suppose I design it for an impulse, instead of impulse, for a step input. In the continuous domain, if I give a step input, what is the corresponding output? K by s into s plus a. Do you all agree? So what will be its time domain output? K by s, okay, 1 by s minus 1 by s plus a into k by a. So the output is k by a e to the ut minus k by a e to the power minus at into ut. Okay. So what will be the discrete domain output? I want corresponding to a step input un, I should get an output yn, which will be a discrete version of this. Is that all right? So once I know, I will take Z transform of this. Z transform of this is known 1 by 1 minus Z inverse. So divide the output by input, that gives me the filter. So let us see what will be the discrete version of this. K by a un minus k by a e to the power minus a t n un. Okay. So what will be the corresponding Z transform? That is yz. This is yn, is not. So yz is equal to k by a 1 by 1 minus Z inverse. This is the Z transform of step function un minus k by a e to the power minus at into n, it is 1 minus e to the power minus at Z inverse. Do you all agree? Therefore hz, corresponding hz is yz by xz, which is k by a 1 by 1 minus Z inverse, k by a I can take out, minus 1 by 1 minus e to the power minus at Z inverse divided by 1 by 1 minus Z inverse, that is the x, is not. Xz is corresponding to un, so I have divided by xz, so that gives me the corresponding transfer function. So k by a, this by this is 1 minus 1 by 1 minus Z inverse by 1 minus e to the power minus at Z inverse. Is that all right? K by a, so 1 will get cancelled, minus e to the power minus, so Z inverse into 1 minus e to the power minus at. Check if this is all right. So this is the step invariance transfer function. So once again, you can take this in a simple block k by a, then actually I could have put k by a into 1 minus c to the power, let me call this whole thing as k dashed by a z inverse by 1 minus c z inverse, where k dashed is k by a into e to the power minus a t, 1 minus e to the power minus a t, and e to the power minus a t is c. Okay. So, k dashed by a, then I have a delay element. Shall I put a delay element here? I can. Okay, z inverse, then the standard one, C and this. So, this is the output. This output will match with the step response of the continuous domain, all right. It will match with this, only it will be in a discrete form. Whatever be the output in the continuous domain, its sampled version will be appearing here. Now, you have seen the technique is similar, but it will not generate the same transfer function. It does not generate the same transfer function as we have got in case of impulse invariance. So, it is fixing, you are fixing somewhere in a particular type of input. If you take the response corresponding to one standard input and try to finalize Hz, that will not give you an identical performance when the input has been changed to, say, from step to impulse or impulse to step. So, that is why these are known as specific invariance, that is either impulse invariance or step invariance. Somebody may go for even ramp invariance. Okay. So, it is specific to a particular signal. These two are taken as standard ones, that is step and impulse invariance. But another thing you observe, you have got two such delay elements, all right, two such delay elements, whereas in case of impulse invariance you had one delay element. If you go for higher order invariance, that is ramp and others, then you will get more and more number of delay elements. Things will be, the single block will be quite complicated. Now, this is all from one factor, all right. So, k1 by s plus p1 plus k2 by s plus p2 and so on. If you have so many factors, then for each one of them you will have such blocks and all of them will be put in parallel, like the earlier case, and then they are to be added. So, you can see the complications will be more. So, this is all about the invariance technique. Now, what are the limitations? Say, let us consider the impulse invariance. What is the difficulty in this? What is the mapping of, say, the poles and zeros? In the S domain, suppose I have a set of poles and zeros, all right. What would be in the, basically what you are doing, a continuous function, all right, which was like this, you are realizing by a discrete domain function like this. You are taking these values, all right. Suppose Fs has roots like this, then I call this corresponding to the discrete version, I call this as some f1s. The Laplace transform of this function is say f1s. What are the roots of f1s? Have you got my point? What will be f1s like? If fs is say k by s plus a, what is f1s? If it is k by s plus a, corresponding ft is e to the power minus at. So, what is f1t? If I call it f1t, fnt as f1t, this is also a function whose values are like this, 0 here, again this. So, f1t e to the power minus ant into un, alright. So, what is the Laplace transform of this? What is the Laplace transform of this? And if you take the Laplace transform, I leave it as an exercise, in the tutorial class we will discuss. If you take the Laplace transform of this, all of you please try this, Laplace transform of this, then what are the roots of those? For k by s plus a, in the original time domain, the root was at minus a, is it not? So, if fs is having a root at minus a, what will be the roots of the discrete version, that is Laplace transform of the discrete version, that is f1s? You will find f1s will have roots at regular intervals here, then again at regular intervals of 2 pi, if you talk in terms of pi, or if you take this as minus omega j omega and plus j omega, then at regular intervals of, that is if there is a root at s0 which is in this case minus a, it can be minus a plus jb also, whatever roots you are getting here, that will be repeated at every interval of omega naught, where omega naught is the sampling frequency. Is that all right? So, S naught plus minus j omega naught, where omega naught or omega sample, I will write omega sample, will be the location of other roots. That means there will be an infinite set of roots, all right, at that same location, and as if they are mirror images, all right, images about, this is pi by t, this is pi by t plus, and this is minus pi by t, that corresponds to omega naught by 2 and omega plus naught omega by 2 and minus omega naught by 2. Then this will be again 2 pi by t, this is a gap of 2 pi by t, they will be at 2 pi by t, again you will have the same roots. It is like this, you walk along the imaginary axis, you imagine you are walking along the imaginary axis, all right, and to your left there is a pole, say at minus 5 on the real axis. On the real axis at minus a, say at minus 5 you are observing a pole. As you go past and your sampling frequency is say 1 kilohertz, then again after 1 kilohertz situation will be same, you will be observing again a pole to your left at a distance of 5. You keep on observing that, all right, you keep on observing that, whether you go this way or go to the minus side, that is minus omega, you will observe an infinite number of poles appear, keep on appearing after a frequency of the sampling frequency, that is 1 kilohertz. You remember, if the frequency response of a signal, if the frequency spectrum of a signal is given like this, and if you keep on sampling at a regular interval, then the frequency response for the sampled signal is repeating after every 2 pi, is it not? It is precisely because of this. That means the number of poles or zeros will be repeating every 2 pi by t. Okay, at every interval of 2 pi by t, you will have repetition of poles and zeros, they will appear identical. So if I take a frequency, analog frequency along this, so whatever I observe in this zone, in this strip, it will be repeated again in this strip, it will be repeated again like this, alright. So it is like this. I have just discussed about a pole, it will be happening with a pole 0, the entire set. Suppose I have 2 poles and 1 0 here, or maybe 1 or 2 more zeros here, or a pole here. So in this entire cluster will keep on repeating. Okay, an infinite number of times. This will be the poles and zeros of the sampled function. If the original function fs is having this as the pole 0 cluster, then the sampled functions, if you take the Laplace transform of the sampled functions poles and zeros will be such clusters appearing an infinite number of times. So if I go from here to here in the z domain, I will make one full circle. Okay. Again from here to here, again another circle. I will keep on making circles. Okay. That means say this point, a pole here is corresponding to this point, then a pole here also will come here. Okay. So aliasing cannot be avoided unless the frequencies, the sampling is very, very high. You cannot avoid aliasing effect in case of impulse invariance method. Alright, aliasing effect means this you cannot avoid, it will be there, okay, unless you do some pre-filtering, okay, some low pass filtering of the signal. These repetitions cannot be avoided, and hence there will be always some aliasing. So impulse invariance method has this limitation, there will be an aliasing effect which cannot be reduced, and in case of bilinear transformation there is a warping effect. We have to take care of that by pre-warping the specifications, and we will be in the next class, we shall be taking up a few examples with all these techniques, and we will also take up Chebyshev approximations and Butterworth approximations. What do they represent? How do you fix up the value of n? How do you fix up the value of n, the order of the filter? Now I will just give you a very brief idea. G j omega, okay, the filter function, if it is given, the rate of fall is given, see it is 1 plus say omega normalized, if I take the normalized value to the power 2n, this is squared. If I take log of this, so 20 log of g is log of this. When omega is very, very small, this will be approximately 1, so log of 1, that is 0, that will be approximately equal to 0 when omega is small. Omega is very large, it will be 20 n log omega, okay. If n is the order, then 20 n log of omega, when omega is of course minus, much greater than 1. and in case of a Butterworth filter, this is normalized, that is whatever is the cutoff frequency, in terms of that we are considering. So, if you know, if the rate of fall is given approximately, suppose rate of fall is very close to say 50 dB per decade, that should match with 20 n. So, what is the integral value of n closest to this? It will be 3. So, if I choose n is equal to 3, then I will get at least 50 dB per decade, the rate may be higher. So, that is how you choose the order n in case of a Butterworth filter. In case of Chebyshev filter, one by 1 plus epsilon square Cn square omega. Okay. So, when this factor is much larger, when omega is much greater than 1, if you have seen those curves, Chebyshev curves, after omega equal to 1, the function Cn will blow up, is not. So, at high values of omega, this will be dominating, so this can be neglected. So, 20 log of g will be 20 minus 20 log of epsilon minus 20 log of Cn. Okay. Now, let us see once again what was Cn. Cn was a polynomial in omega. Okay. What is, if you just look at Cn, all the Cn's, for example, C3, it is omega 3 4, C2 it was omega square 2. So, since we are taking omega greater than 1, in a polynomial I will take only the highest term, it will be approximating to this value, okay, highest order of the polynomial term. So, it will be, if it is 3, it is 2 to the power 2. So, it is Cn will have 2 to the power n minus 1 and omega to the power n. Is that all right? So, Cn will be 2 to the power n minus 1, then omega to the power n. Okay. So, 20 log of Cn, this will be giving me minus 20 log of epsilon minus 20 log of this will give me n minus 1 log of 2 minus, how much is it? 20 n log of omega. Is that all right? So, okay, let me take it here. This is omega equal to 1. So, from this point onward, I am drawing only the asymptotes. Okay. So, it will be here close to 0. 20 log of epsilon, epsilon is a fraction. So, log of a fraction will give me a negative quantity, negative and negative will give me positive. So, 20 log of epsilon, though it is minus, but actually its absolute value will be plus, is it not? Epsilon may be say 1/4, 1/5. So, that will give me 20 log of epsilon, and then 20 n log omega, 20 n log of omega. Okay. So, that will give me a slope corresponding to 20 n dB per decade, okay, which we got for Butterworth filter. Suppose this was 20 n dB per decade, 20 n dB per decade, log of omega means, that gives me 20 log of omega means 20 dB per decade. So, 20 n dB per decade. So, this is the slope, add with that this quantity. So, this slope has to be shifted up. If I have only this term added with this, so 20 n dB per decade fall minus, so it will be falling, minus this, in absolute term this is a positive quantity, so it will be shifted up. and then 20 into n minus 1 into log of 2 is 0.3, 0.3 into 20, that gives me 6. So 6 into n minus 1. So from this point, this position, again bring it down by 6n minus 1 dB. Okay. So this will be the final asymptote. Is that all right? So the Chebyshev polynomial will be generating a function which should follow asymptotically this curve. All right. So from there you can find out n. Epsilon is formed from the ripple width. Ripple width is 1 by 1 plus epsilon square, that we have seen. So if the ripple width is given, you know epsilon. Once you know epsilon, you know this 20 log of epsilon, and then from the given characteristics you know what should be the rate of fall. Okay. So n can be selected from there. So this is how we select the specifications in terms of n and epsilon in case of Chebyshev filter. So we will stop here for today. We will take up some problems in the next class. Thank you very much.